This is the second part on how to determine continuity and discontinuity using limits. Okay, so the instructions for the two examples we're going to be doing are for us to discuss the double-sided limit and continuity of the given functions at the specified x values. Okay, at the specified x values. Okay, so for question 1, let's say we have the piecewise defined function given by x plus 3 when x is not equal to 2, and then 7 when x is equal to 2. And then we're doing this, we're discussing what's happening, the limits and continuity at x equals positive 2. To get started, we're going to look for the left-hand limit, right-hand limit, and value of function, and then we can discuss after that. So let's, to get ourselves organized, we want to draw a number line to have a visual as to what's going on. So if you take a look at this, we have a line missing a point and then a point. So let's break it up. We can call this 1 and call this 2. The break happens at x equals 2. So how can we capture what's going on in this piecewise defined function on a lumber line? X plus 3 is everywhere except x equals 2. So for the red, we have an open circle and everything to the right and to the left of that open circle. Okay, so everything to the right and everything to the left of the open circle, x plus 3 is active. Okay, but if we go to the point itself, so let's label what's going on here. So we have x plus 3 and x plus 3. It doesn't matter if you're coming from the left or if you're approaching from the right. You're still going to have the same function x plus 3. Okay, but when you're on that point itself, what's active is this constant right here. It's just a point, 7 right on the point. Okay, alright, now let's go ahead and take a look at the limits for this problem. Let's start with the left-hand limit. So for the left-hand limit, we're looking for the limit as x approaches 2 from the left of the function. So when you're approaching 2 from the left, x plus 3 is active. So this problem basically becomes the limit as x approaches 2 from the left of the quantity x plus 3. And then since this is a finite limit, we're going to substitute first to see what happens. When we substitute, we have 2 from the left plus 3. This is equal to 5 from the left, and this number is approaching 5. So this is your left-hand limit. Now we're going to proceed by taking a look at the right-hand limit. So the right-hand limit basically is the limit as x approaches 2 from the right of the function. Now, if we are to the right of 2, if we take a look at our number line, we can see that the red function is also active. Both from the left and right, the same function is active except when you get to the point. Okay? So this is going to become the limit as x approaches 2 from the right of x plus 3, because that's what's active. Okay? And then we plug it in. We have 2 from the right plus 3, which is equal to 5 from the right. And the number that you're approaching here is just 5. So with this information that we have, we can conclude that the limit exists at x equals 2 because from the left and the right, you're approaching the same value, y value, which is 5. Okay, we'll write that in the conclusion. Let's take a look at the value of the function, POF. The value of the function is basically what the function is evaluated at that breakpoint, f of 2. Okay? Now let's take a look at the graph we have here. We can see that at 2, the function attains the value of 7. So f of 2 is simply going to be 7 evaluated at x equals 2. When you evaluate 7 at x equals 2, you're going to get 7 because 7 is independent of the x value. It is a constant function, which is always 7. Okay? Now let's discuss the limits and continuity of this function. Let's start with limits. What do we know about the limit here? The limit exists at x equals 2. What's the justification? How do we know that the limit exists at x equals 2? Well, it's because the limit because the limit as x approaches 2 from the left of the function is equal to the limit as x approaches 2 from the, if this is from the right, is equal to the limit as x approaches 2 from the left. These two are the same. Okay? So this is the condition for the limit to exist. Basically, the right-hand limit is equal to the left-hand limit. That's enough to conclude that the limit exists at x equals 2. Okay, let's take a look at the next conclusion that we can draw, which has to do with continuity. Alright, so concerning continuity, the function is not continuous. Okay, so the function is not continuous at x equals 2, is not continuous at x equals 2. Why is that the case? Well, it is because the left-hand limit is equal to the right-hand limit, which means that the limit exists, but these two must be equal to the value of the function for the function to be continuous. But these two are not equal to the value of the function, which is f of 2. This is 5, this is 5, and this is 7. Okay? So, this is, what did we get for these two? 7 or? Yes, that's correct. Alright, 5, 5, 7. So basically what we have here is that the left-hand limit is equal to the right-hand limit, but these two are not equal to the value of the function. In order for the function to be continuous, these three must be the same. Okay? Now the type of discontinuity that we have here is what? We have a point or removable discontinuity, point or removable discontinuity. Why do we have a point or removable discontinuity? Well, it is because the left and right hand limits are finite and equal, but not equal to the value of the function. Okay? So they're both pointing to the same thing, but what they're pointing to is basically an open circle. Alright, so let me give you a visual of what's going on. It's not necessary, but it definitely helps to understand the whole scenario. Okay, so let's go ahead and sketch the graph real quick. So we're going to draw the graph of y equals x plus 3, and then we're going to take a look at the situation. So this is just a visual representation of what's going on. So we have y equals x plus 3. In this case, we have y equals mx plus b. M is 1 over 1, and b is 3. So we're going to start from 3, and then we're going to rise 1 and run 1 in order to get the second point. Alright, let's graph it. So we start from our y-intercept, 1, 2, 3. That's the first point. We're going to rise 1, run 1. That's the second point. Keep rising and running. But at 2, what happens is that we have an open circle. Right? So this is the line that we're looking at here. This is a function. This is one part of the function. Okay, but at x equals 2, the function attains a value of 7. Okay, so we have 2, 3, 4, 5, 6, 7. So at 7, you have a closed circle right here. So if you take a look at this, you can see that the left and right limits are going to the same point, but the value of the function is somewhere else. Okay, so that's why we have what we have. Now let's take a look at another example. This will involve a different type of discontinuity. So for question number 2, what if we have the piecewise defined function given by 5 over x plus 2 when x is greater than negative 2, and the square root of x squared plus 12 when x is less than or equal to negative 2. Alright, so before we get started with the right hand limit and the left hand limit, we're going to sketch a number line and see what's happening where. Okay? Alright, so number line sketched. For this problem, we're looking at x equals negative 2. That's the point under consideration. So we're going to do this by labeling the functions. Let's call the one on top 1, and then the one on the bottom 2. Alright, so for greater, the break happens at negative 2. Okay, we have to the left is function 2, and to the right is function 1. Let's do function 1 first. Function 1 is an open circle because there's no line here, and then we're going to be heading towards the right direction. Okay, that's function number 1, where x is greater than negative 2. The function that's live here is 5 over x plus 2. And this is when you are approaching negative 2 from the right. Okay, this is from the right direction. Alright, Different story from the other side. From the other side, we have a closed circle for function 2, and we are going in the left direction. So if you're on the point or anywhere to the left, what's going to be active is the function. So for x is greater than, less than, or equal to -2, what's active is the function square root of x squared plus 12. And this is applicable when you're approaching 2 from the left, -2 from the left direction. Okay? Alright, so we have everything set up. We're ready to take a look at the limits. Let's take a look at the limits. Let's start with the left-hand limit. So for the left-hand limit, we're looking at the limit as x approaches -2 from the left. Okay? So the limit as x approaches -2 from the left of the function. So for this one to the left, we can see that function 2 is active. So this is basically the same as the limit as x approaches -2 from the left of the square root of x squared plus 12. Okay, so since this is a finite limit, we're simply going to substitute and solve and see what happens. So we have -2 from the left squared plus 12. If you square -2 from the left, it's going to become +4 from the right. You square both the direction and the sign changes. You add that to 12. And then that simplifies to the square root of 16 from the right. Square root of 16 from the right is 4 from the right. The number that you're approaching is 4. Let's take a look at the limit from the right-hand limit. So the right-hand limit is as follows. We're taking a look at the limit as x approaches 2 from the right of the function. Now when you're approaching 2 from the right, let's go back to our number line. The red function is active. Okay, so this basically becomes the limit as x approaches 2 from the right of the red function, which is 5 over x plus 2. Okay, now since this is a finite limit, we're approaching -2, sorry, so approaching -2. Let's fix that. So this is a finite limit. We're going to substitute. So let's go ahead and substitute. We have 5 over -2 from the right plus 2. Okay, so what is -2 from the right plus 2? To give us an idea, let's go ahead and break this down. -2 from the right. We make a number line. We have -3, we have -2, and we have -1. So we are coming to -2 from the right. If you look at the center here, this is -1.5. If you get really close to -2 from the right, this is -1.99. And if you get really close, you have -1.999 infinite number of times. So this basically becomes 5 over -1.99, an infinite number of 9s, 99 plus 2. When you add these two together, you have 5 over 0.00, an infinite number of zeros, 0, 1. Okay? And this can be written as 5 over 0 from the right. So 5 over 0 from the right, 0 from the right can be written as 1 over infinity. And then when you multiply 5 by the reciprocal of the denominator, infinity over 1, 5 times infinity is just infinity. Alright, now let's go ahead and take a look at the value of the function. But before we do that, we can see that the left and right hand limits are different, so the limits will not exist. Okay? Alright, value of the function. Value of the function is f of a, so f of negative 2. Okay? So f of negative 2 is going to be, which function are we looking at? For the closed circle, we're looking at the blue function, the square root of x squared plus 12. So we're going to be looking at the square root, let's color code this, the square root of x squared plus 12 evaluated at x equals negative 2. Okay? So this simply means you take this function and you plug negative 2 into it. If we do that, we have the square root of negative 2 squared plus 12. And then you can simplify that. This becomes the square root of 4 plus 12. And this becomes the square root of 16, which is just 4. Okay? Now let's write our conclusions down based on what we have. So our conclusions are as follows. Let's talk about limits first. What do you know about the limits? The limit does not exist. Okay? The limit does not exist at x equals negative 2. Why? Why does the limit not exist? Because the left-hand limit of the function was not equal to the right-hand limit. Left-hand limit, let's change that sign to minus, is not equal to the right-hand limit. One was 4, the other was infinity. So if their limits are different as you approach a point, then the limit, the double-sided limit, there does not exist. Okay? Alright, so let's take a look at continuity. What do we know about the continuity of this function? Well, the limit does not exist. The function is automatically discontinuous. Okay? So continuity, the function is not continuous at x equals negative 2. Why do we say that? Because the left-hand limit of the function, the left-hand limit, even though it's equal to the value of the function, these two are the same, right? But is that sufficient to conclude continuity? It's equal to the value of the function, but these two are not equal to the right-hand limit. So because of this lack of equality, the function is not continuous. We now have to classify the discontinuity, okay? So what type of discontinuity do we have here? We have to describe that. We have an infinite discontinuity. Infinite discontinuity at x equals negative 2. The condition for this, as we went over in part 1, is that if at least one of these limits is equal to plus or minus infinity, then that means you have an infinite discontinuity. So we have an infinite discontinuity at x equals negative 2 because, in this case, just the right-hand limit. The right-hand limit as x approaches 2 from the right, is equal to infinity. So we have an infinite discontinuity here.